Hello everyone, my name is Michael, and today we're going to take a look at something ransomware related. Now today I have a sample that is actually a decryptor from the criminals. Unfortunately, this victim paid for, paid for decryption and received an executable from them. And there's a couple reasons we'd want to take a look at the decryptor. The most common may be we don't have access to the original malware, perhaps. Maybe it's a new sample that no one has found a sample for yet. So the decryptor can still give us some information on how the operations work, maybe what cryptographic functions it's using, what file format. So it still can be very useful to reverse. Sometimes I also will reverse it in order to make my own decryptor because the criminals may have a bug in their decryptor, or it's not very user friendly, or I might want to add some extra features to help the victim out. So in this case, let's go ahead and run the Decryptor. Now we'll see this is a Hermes 2.1 decryptor software, and they give us a few options here for decrypting a single file or starting full automatic decryption. I'm assuming number 2 is going to just enumerate over all the drives and look for all files and try to decrypt everything, which could be very slow for this example. So I'm going to go ahead and hit 1, and it says you need to write the full address of the file. This can be very not user friendly, especially you might not want to just gung-ho go and decrypt the whole system. You might want to decrypt a folder first to test. So already this would give me some incentive to maybe write my own decryptor. So I have some sample files here that are anonymous data from that same victim. I can actually drag that into the console here. Luckily, I don't have to type it out. So we'll hit enter. We'll say, okay, well, that was pretty quick. Choose next file. We'll see, okay, it looks like it's been decrypted. At least it doesn't have the extension. Let's take a look at that in the Hex Editor. And yeah, this looks like ASCII data with, it's a CSV, so I'd expect there to be commas, and this is a new line character, so I guess that worked. If we compare it to, this is just a copy of it, we'll see, this was very obviously encrypted. Lots of garbage there. So let's go ahead and close those files. Now let's take a look at this in PE Studio once again, just for a quick static analysis. We'll kind of go over just a couple points on this one. So we'll see signatures, Visual C++. It's an executable console app. It's 32-bit. The entropy is low, so it's probably not packed. So this means we get to go into a disassembler to analyze it. I'll take a quick look at the libraries, just so you can see Advanced Windows 32 Base API, the ADV API 32.dll. This DLL actually contains all of the CryptoAPI functions. If we go to imports, we can confirm that. We can sort by name. Let's take a look. So we have crypt acquire context, we have crypt decrypt, crypt destroy key, crypt import key. So that can already tell us that it's going to use the crypto API. It usually can be pretty simple to kind of see what is going on when it's using this API, luckily. So we'll go ahead and I'm going to go ahead and use a disassembler called IDA. There is a freeware version. That's the one I use since I don't work for a corporation. Once again, disclaimer, I'm not a professional malware analyst. Just a guy that likes to try to reverse ransomware on my own. So we're going to go ahead and open this up. It can definitely be assembly can be very intimidating for a beginner. I'm still learning how to use this tool, definitely. So apologies if I offend anyone trying to stutter through this. So when we first open up IDA, it's going to take us to the entry point. This is where the where the malware is going to start running. As soon as you execute it, this is what happens. Usually there's not too much useful stuff here in my experience, at least, unless it's like packed or something. You'll see this is where you'd maybe try to unpack it. We'll take a look down here. I've already kind of gone through this executable on my own. to try to speed up where I'm going. I did identify most of what's going on here is in this one function that I called main function. The rest of this is probably like just set up maybe the actual main function. We'll see there's a get command line. So that's maybe if there was parameters passed, we'd maybe look into what they do with those parameters. But when you first launch the executable, I don't think it took anything, or it didn't ask for us to, rather. So we're going to take a look at this main function, and this is where I found the strings that we saw when we launched it. We'll see Hermes 2.1 Decryptor software, and we'll see they're just using the console command color to change it. The background black, foreground A is green. The way that I originally located this is the strings window. Once again, just like PE Studio, we can look at the strings, and then I just found, some of the interesting strings we wanted to see. Decrypt start, Decryptor software. If I double click on that, it'll take me into the actual hex of it, kinda. If I press X on my keyboard, that takes us to XREFs, cross references, and we'll see where that was actually referenced, and that takes us back where we were. A quick newbie tip for IDA. I think by default, for some reason, the strings window is not normally there. You can get that by going to View, Open Subviews, and then Strings is right here. There's also a couple of other ones here, names, and some of these I closed because I don't really use them. So we'll take a look here. Here's all those strings. This is probably like a printf or something, just based on how it's used. So we'll see. I've renamed this variable input number because at least I think that's where your input gets saved to. So we'll see. All right, so first off, we compare it to 1. And the first option was decrypt a single file. And if JZ is a jump condition, basically compare, if 1 equals 1, compare will set a 0 flag. So just like in programming, where you use the compare, like str compare or something like that, if 2 inputs are exactly the same, the output of the function will be 0. Otherwise, it'll be a 1 or a -1, depending on which one is different, or greater than or something. So in this case, 0, if it was successful. So if our input is 1, we're gonna go this path, which we can get a little hint as to that. If I double click on it, it takes us down to there. We're gonna look at that later. If we press number 2, so if it's not 1, we go to the red one, which comes to here, compares it to the number 2. If that doesn't work, we compare it to number 3. So we can actually see the paths for 2 and 3 come down here as well. So they have like a hidden menu option. Number 3 does the same thing as 2. And then we'll see if we didn't enter a 1, 2, or 3. Incorrect. Try one more time. I think it just basically loops back up. We'll see this thick line kind of loops back up here after it does some comparing, some other mess. So we'll take a look down here as to where when we hit 1 or 2, or apparently 3, we'll come down to this block of code here. Now, it looks like get module file name. Okay, so this variable file name, we're going to open a file. Desired access, this is like open access. Create a file. Create file doesn't always create a file. Depending on what flags you pass it, it actually is just used for opening a file in general. So we'll see the file name. I had traced this back earlier in a debugger, and I found that this is actually the executable path. So this is actually the file name of our executable. So if I ran it from my desktop, it would have this path /decryptor.exe. So apparently we're going to open our own executable here. We're going to get the file size while we got the handle. We're going to set a file pointer. So we're not reading from the beginning of the file. We're going to go somewhere else in the file. Now this is a very large, what looks like a very large hexadecimal number. For example, if I hit the H key on my keyboard, I can turn that from hex to decimal. Now that looks like a very big number for set file pointer. You know, not many files are going to be 4.2 billion bytes. So this is actually a negative number in hexadecimal form. And the way that works is because it's you treat it as a signed 32-bit integer, and this actually wraps around to the negative part. So if we actually copy this, take it into a calculator, take it to hex mode. I'm in the programmer mode. The way I went to this is view programmer, and input hexadecimal. Let's go to keyword is a 64-bit, as you see here, 64-bit number. If we go to dword, that's a 32-bit number, so a signed integer. We'll go to decimal, and we'll see it's a negative 100 or 1,172. You'll see I've added a comment of that since I already calculated that before. So we actually since we're passing a negative to set file pointer, what that does is it does relative to the end of the file. So we're going to read, basically, we're going to point to 1,172 bytes from the end of the file. And then if we go to read file, we're going to read that same amount of bytes. So we're basically reading the last that many bytes from the file. And it's going to go into this buffer. As we see here, the arguments for read file, the first is handle to the file, which was just ESI here, which was just our handle that we got from create file. And our buffer is being used in this register, which is actually loaded, as we see right above this variable. So this is a local variable buffer that we're going to use for whatever we're reading from our executable here. So we'll take a look down here, and this crypt acquire context is going to be kind of our setup. This is where we acquire the context in order to do anything with the crypto API. So we'll see here, this is pretty standard for, well, kind of standard for how this function is used. They kind of go overkill with it here, but typically you will see it called at least twice with different flags. I've kind of filled in what these flags are. We have the flags and the provider type. We'll see the provider type each time is provider RSA AES. So that already can give us a clue that we're probably going to be using RSA and or AES. Now the way that I found what these flag values are is luckily Microsoft's pretty public on their function, you know, because obviously developers have to be able to use these functions. So we'll see here, sorry, if we go back to here, okay, so crypt acquire, we'll see these are the flag values. Now unfortunately they don't just show the hex value here too, they just show this is a constant that you'd use. Now I cross-referenced this with the source code. So I just looked up the wincrypt.h file. This is the header file that you would include as a developer to use these functions. We'll see here, I just searched for that constant, and it has value f00000. We'll see if I take a look back here, our flag is actually hexadecimal 10, which is delete key set. And we can come back to here, and if we were really interested in a wall of text here, we can see deletes a container. So this very first call, they're just deleting whatever context there is. That's kind of an odd move, but okay. And then the same thing with this 24. I just looked up. I just looked up in here what those values are in the header file. So it is typical that they'll call it, typically one of these blocks would be what I'd call normal. You'll call it the first time to try to get a new key set, and if that fails, you'll probably call it a second time to try it with the different flags, because most of the time if the first one fails, it's probably like a permissions thing. So you can still get a context using different flags. But they call it a whole bunch of times here. So, okay, so then we'll see, once again, we had that buffer, this same variable buffer that we read, once again, this same value, 1,172 bytes from the end of our own file, and we're going to import that as a key. So that can already tell me that the whatever this 1,172 bytes at the end of our executable is a CryptoAPI blob, because the import key function relies on a certain format called the blob format. If we take a look here at our parameters for import key, we have provider, that's just our crypt acquire context. Okay, so the PB data is a byte array that contains a public key blob header followed by the encrypted key. Big hint right there. So we have an encrypted key, possibly. Key blob is created by export key, blah, blah. This is probably how it was used in the ransomware. And then next parameter is just how long of this buffer is. And then this is a way you can actually import a key and decrypt it using another key, which we'll actually probably see that later. We have some flags. We'll see here. Here they're not using a public key because this spoilers is the public key that we're importing. The flag 1 is actually crypt exportable. I know that one. That just means that later on, if we wanted to, we can export this key. They don't, so they really didn't have to set 1 here. So we're going to import this key, and apparently if that fails, then we're going to ask the user for another file or something. Alright, so if it succeeds, then we go to some extra... Oh, okay, I think I see what's going on here. I may not have realized this before. The EBX register here, I think, is our input. Yeah, that's our input number still, all the way down here. So this is where they determine whether you had selected 1 or 2 or 3. Okay, so 1 is going to take us over here, and we're going to get logical drives. And we're going to get drive type. I'm not sure what 5 is. And we're going to probably start enumerating over those drives. Okay. So if we had actually selected 2, or was it 2? Okay, 1 is per file. Okay. I'm getting these backwards. My apologies. Alright, so if it is 1, okay, so if we're doing a single file, we're going to come over here. Okay, so here's our prompt where it said, please write the full address, for example, C/ whatever, choose 0 for exit. Okay, so this is probably like a print function. Okay, so let's follow this down. It's actually this line. We're going to come all the way down here. And that's actually going to be a loop condition. Whoops. This is the annoyance when it's a really big function and they don't break it up. Okay, so where was that? I want to see where that OK string was, because that probably tells us when the decryption was finished. Let's see. Actually, taking a look in the strings here, we can see the way they rename the file after it's done is they just use the rename command at the command line. It should be pretty close here. Choose next file. Okay, that's probably when it's done. What I did was I hit X for cross references. Go to here. Okay, choose next file. Okay, somewhere nestled in here, they do call another function. Okay, there's our OK. There we go. Not sure why that didn't show up in the strings very easily, but all right, so we'll see here. We're going to go to the decrypt function. Now we're going to pass in a couple parameters here. This is a function they wrote, so it doesn't always show me all the parameters, but it looks like it did kind of rename a couple things for me. There's existing file name, so that's we're going to pass it the file. We're going to pass it two providers here. Now that's probably because they're using one provider for AES and another provider for RSA. I'm not quite sure. I'd have to look at it a little more deeply. But I renamed this function Decrypt File because it seems where they're actually decrypting one file. Now we'll kind of snoop around here. So, all right. So we have create file. Once again, this is I think this is open access. We could look at documentation for create file and see what these desired accesses are, but I'm pretty sure it means open. And all right, so if it fails, close the handle. If it succeeds, go over here, get the file size. And once again, we have a big old mess of functions all in one function. All right, so here we go. Setting a file pointer, reading hex 32, which is 50 bytes. Okay, so it's going to do some stuff to the file. Here's a sleep for some reason. Okay, so I'm not too interested in what's going on there. What I'm looking for is going to be where they're using another key. And I've marked it here for myself since this is a tangle mess here. Okay, so we'll see. All right, so this is our function where we have the key, or we have the file rather. And we're going to set a pointer. Once again, we're going to have a negative hex number. So this is actually negative 16. Okay, so we're reading part of the file. Okay, here's where I'm looking for. All right, so we're going to read, apparently, we're going to read 268 bytes from in the file, which if I recall here, should be... okay, this is probably a conditional to see if the file is like too small, then it changes how much of the file it's reading. So here we're reading 268 bytes. Keep losing focus there. And we're actually importing a key here. So I've already identified this as actually our step where we're importing the AES key. Now there's something interesting you'll see here. This PubKey parameter is actually filled with this PubKey variable. Now that is actually our RSA key. So the way this works, if we go back to our cross-reference up here, where we import the RSA key, this provider in EDX is our PH prov. That's just kind of standard what you name the variable. So if we take a look back here at import, this is where we can see if we pass it a public key. This is a handle to a cryptographic key that decrypts the data. So what we're importing here in PB data is an encrypted blob. And we're going to, as we import it, it's going to be decrypted using whatever key we defined in here. So what we have here is an AES key that's being decrypted by RSA. This is very, very standard for not just ransomware, but a lot of cryptographic usages. So we'll see here if it's encrypted with a session key. This parameter contains a handle of that key. Okay. You can read more on this documentation, and then they have some examples at the bottom, or you can just Google some samples of this. So that basically tells us exactly how they are storing keys. It seems like there's one key per file, and there's like a master RSA key that unlocks all the individual keys. Let's jump back to our AES key. All right, so we're importing that key. and we're going to have it in this register, which is this key. So this PH key is what we're going to use to decrypt a file. Where am I on the graph? Okay, I'm way over here. Now, if we take a further look back, now we're going to set the file pointer back to 0. We're going to go back to the beginning of the file. And it looks like some virtual alloc. We're probably going to like build a buffer to start reading. And I'm going the wrong way on the tree. Okay. Set file pointer, read. Okay, so here we read the file. We destroy a key. So when we're done with the key, we destroy it. It's just standard practice to make sure you don't have a memory leak. Okay, so here's the decrypt. So we're moving this PH key, and we're going to use that in the EDX register, which is our H key. This is what we're passing to crypt decrypt, and this is the bread and butter function, I want to call it. So we're going to use that key, and we're going to decrypt what's in this register, which I'm assuming is what we're messing with. Yeah, okay. ESI is the buffer that we read from. Okay. So from this information, we can already tell exactly how this decryptor works. So at this point, it's just a lot of boilerplate code to kind of recreate this. But I can actually, you can read through the documentation here to see exactly how these functions are used. I'm going to go ahead and take a look at this decryptor in a Hex Editor. So we already knew at the end of the file there's something interesting. Let's scroll through here. And there we are. Okay, RSA2. This is something that I would, recognize as a key. So we have 0702. 07 is the blob type. I'll kind of pull up the documentation for the blob type. So I believe this is a simple blob. CryptoAPI. Base provider key blobs. Okay, here we go. So this documentation, once again on Microsoft's website, will tell you exactly how to read this blob. So I'm going to go ahead, and this is just some type of delimiter, it looks like. Let's go ahead and copy that all. Let's just make a new. Yes, I know it's going to change the file size. Oops. I need to close that one. So let's go ahead and save this. This is our RSA key binary. Okay. So let's take a quick look at how this blob is formatted. So we have a public key structure. Then we have, I'm sorry, that's a public key blob. I know for a fact this is a private key. Even based on the way we're using it, you have to have the private key to decrypt what the public key has encrypted. That's basically how asymmetric encryption works. So we have a private key blob. So we actually have the public key structure, which is the same as the public key. And then we have all this stuff about this is the public key format. Then we have the modulus, the prime, the exponents, the coefficient, private exponents, all that stuff. This is all basically how RSA works. So we can see that's why this blob is so big. There's a bunch of very large numbers that are basically represented in hexadecimal in this. So what we want to take a look at is this public key structure, which it seems to be what it starts out with. Indicates a key's blob type. All right, so here's the beginning here. So we have a B type. As we see, it contains what type of blob it is, which tells us basically how to interpret the rest of it. So we have a plain text blob, key blob. We can see private key blob. This is used for public-private key pair, aka asymmetric encryption. Pretty much you'll always see this was RSA. We also have public key. This is probably going to be just the public key. That would be what's in the malware itself. And then we have simple blob, which is usually what you see an AES key in. So we take a look back at our key here. We have 7, which is the private key blob. So that tells us what type of key it is. Version, blah, 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 should always be number 2. And it is. Okay, next part is very important. This is the algorithm that is used. And if we take a look back at our structure here, alg ID, actually, there's a reserved byte of 0. Let's take a look here. So, all right, yeah, must be set to 0. All right, so our key algorithm is going to be what type of key this is, what algorithm it represents. So if we take a look at this alg ID, it's kind of like a enumerable. They have a bunch of constants here. Now, because of, I believe it's the Indianness of how this is represented, the bytes will be kind of flipped from what you see here. So this is actually, this is our D word that represents the algorithm. So A4, I would just look for A4. And you'll see it's kind of flipped, just based on how it's represented. These 2 bytes, you flip it over here. So we'll see RSA key X. Okay, it's a public exchange algorithm. So we can tell this is a private RSA key at that point. Further on, if we go back to our private key structure, once again, that was just the beginning of it. We have back down to the private key. Let's see. So we'll see here part of that structure once again. RSA PubKey, magic must be this value, as we'll see here. So basically, a public key has this ASCII of RSA1, and the private key should say, there it is. Magic must be this 32 blah 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 hexadecimal of ASCII of RSA2. So once again, that's how we know this is a RSA2. Or it's a private key because of that RSA2. You can further then, if you want to, read through the structure here and how many bytes are what, and pull out the exponents and all that fun stuff. This is why I wrote a program that does this. Once again, when I release this, I'll make a video on it. But if we go to our key, pull this all out, plop it in here, we'll see once again it confirms it's a private key blob, it's an RSA key. Further on, because of that structure, you can actually tell how, what size RSA it is. So this is actually our key with all the exponents and all that, and we'll see it's an RSA 2048 key. So right here we can tell we can't break that realistically. So let's take a look. The other thing was that they had a key blob in the encrypted file. So if we take a look at one of our encrypted files, they were reading at the end of the file. Once again, we have a Hermes file marker here. That's one way of identifying this ransomware, other than the extension of .hrm. We'll see here. All right, yep, this looks like a crypto blob. And once again, the 1 is a simple blob, 2 is the version. These 2 bytes are reserved. This 1066, we can actually look that up once again in the algorithms here. 1066, oops, actually flip it, 6610. And we'll see, okay, this is an AES 256 key. And furthermore, if you look further down in the documentation of the encrypted blob, I believe, because it should be a simple blob. Sometimes I find the docs a little hard to go through sometimes. Okay, so this is where we're at. We're at that public key structure, algorithm, encrypted key. Okay, actually, I'm sorry. What we looked at, once again, this beginning part here with the AES saying that's an AES key is the public key structure. Now, there's a second algorithm ID here. And as we'll see here, it is once again our A4 number, which matches up here, the 0A40000. So what that means is this key is encrypted with RSA. So we have an AES key encrypted with RSA. And once again, I can take a look at that in my blob analyzer. Paste that here, and we confirm it's a simple blob, AES 256, encrypted by RSA. Now the length in this context is how long the encrypted key is, and we'll see this is what's encrypted. This is what's actually encrypted by RSA. Now I have a extra little function. We can kind of, without having to write code, I can kind of test that I have, this inner workings in my head correct. So if we take this encrypted blob that was at the end of the encrypted file, and let's grab our RSA key. I can go to decrypt blob, paste that in here, and here's our plaintext blob key. This is actually the key that was at that final crypt import. This is what key is basically going to be used to actually decrypt the file. So we'll see it's plain. Now it's a plain text. It's AES 256, no encryption, and we'll see the length of the key. This is actually the plain text key that we can actually use directly. It's 32 bytes, which matches up. AES 256 always uses 32 byte keys, aka 256 bits. So we can actually take this blob. Let's go ahead and open up that encrypted file. So over here we have the encrypted file. Let's go ahead and paste that blob in here. Tell it that's a blob. We'll see we automatically selected it's an AES key. And we need to account for padding is not going to be correct in our case. Let's just decrypt a couple blocks here. So we'll see this actually looks like our decrypted data. Let's do a little more. Let's do 256 bytes. And let's go ahead and save that. Decrypted CSV. Let's take a look at that in the Hex Editor. And it looks like we've decrypted it on our own. So once again, like I said, I would maybe make a decryptor that's a little more friendly. It lets you, has a graphical user interface, lets you select a folder to test with or something. But in this little, this little analysis here, we can see exactly how the decryptor works, and that gives us more information. Thank you for watching, and let me know in the comments if you have any tips for me in IDA. Since, like I said, I'm a very beginner, so I think I can make more beginner relatable videos with some interesting samples here. Tune in next time for some more interesting ransomware analysis. Thank you.